now we will start using the parsing techniques that we have learned to actually build the abstract syntax tree. So remember from the earlier lectures, we talked about the different stages in a compiler. We have the front end, the optimizer, and the back end. And we said that the front end takes the high-level representation, the source code in the high-level language, and the output of the front end is what?
The
abstract syntax. So today we will learn how we can construct the abstract syntax tree based on the parsing techniques that we have studied. So this is the familiar classic expression grammar with the assignment. So I have also added the assignment to it. And let's now do the parsing for this example, and then see the corresponding abstract syntax tree. So let's do the parse for this. So this is an an assignment. So it's a goal, and the goal is an assignment. And this assignment is an identifier. Identifier equals expression with semicolon. And then this expression is what? The expression is this, and this expression consists of how many terms? 2 terms, right?
Yeah.
Everybody was good at doing the derivation in the test, by the way. So everybody, almost everyone in the class did this. The derivation did correctly. So it's expression plus term. And in this case, the expression is what? Is a term, right? And this term is term times factor. Okay. And this term is a factor. And this factor is an identifier, which is what? The A.
Yeah.
So this identifier here is the X. This identifier is the A. And this is times factor, and the factor is an this factor is not an identifier. This factor is a number, and this number is the 3. And this term is a factor, and this factor is an identifier, which is a B. Okay? So far nothing new, right? So we know how to write this parse tree or derivation tree. So this is the parse tree. Or the derivation tree for this expression. But what we want is not the parse tree. We want the abstract syntax tree. And what's the abstract syntax tree conceptually? The abstract syntax tree is basically this parse tree, but with only the operations that matter, for code generation purposes, or the operations that correspond to real actions. So we would like to keep the nodes that correspond to real actions and get rid of any node that corresponds to just grammatical substitutions. Substituting a grammatical symbol name for another. For example, this edge here, we are here, this is just a substitution. Here, there is no action between term and factor. So, whether you look at it bottom up or top down, if you look at it bottom up, then this factor is reduced to a term. Or if you look at it as in top down, this term is expanded into a factor, but this is just a matter of naming. There is no actual operation that is happening. What are the actual operations? The actual operations are the arithmetic operations, multiply, add, okay, and there are other operations.
Equal the assignment.
This is the assignment operation, okay. And what else? About the leaves. So these leaves, the identifiers and the numbers, now we should start thinking in terms of code generation. So in terms of code generation, this will result in generating some code because these, if this is a variable, then this variable, in order to use it in this expression, what do we have to do? What kind of code do we have to generate?
A memory reference.
Yeah, exactly. So we have to bring it from memory possibly using a load instruction to bring it from memory. So these leaves are also interesting. So in terms of constructing, since our objective is to construct a data structure that will help us in code generation, these are the nodes that we care about. And everything else can be abstracted away, right? So we can, our abstract syntax tree in this case is going to look like this. There is an assignment node, and this assignment node assigns this identifier. So this is an identifier node, assigns it to an expression, but this expression is just a name. In this case, this expression is the add of an expression and a term. So the actual operation here is the add. So what does this mean? It means that this assignment is assigning the result of this add to this variable. It's an assignment that assigns the result of the add operation to this variable. And now, what does this add operation, where does this add operation come from? It adds two things. It adds the result of the multiplication to this identifier. The result of the multiplication to the identifier. Okay, let me just move this a little bit. I'm going to just redraw it, so I'm not going to change it. I will redraw it because I need this space here. Okay, so I'm going to do assignment and then identifier, add, multiply, identifier. And what does this add? This multiply, it multiplies the identifier with the number. As we will see in the next lectures, when we have an abstract syntax tree, so this is abstract because we abstracted away. We got rid of all the nodes that correspond to grammatical symbols. In terms of code generation, after we do the parsing, after the parsing is done, we no longer care about grammatical symbols. We care about what this means in terms of actual operations because we want to generate code. And generating code here, in this case, can be done, as we will see, in a straightforward manner. So for this identifier, if we put the names here, X, A, 3, and B. So the corresponding code, for this identifier node, there will be a load. So we will be loading X into some register, and then loading A. I'm sorry, loading A. By the way, so this is where the actual code generation will start, loading A into a register. Then for this number, we do a load immediate. load immediate of 3 into another register. Then, this node, what do we do here? Multiply. Yeah. Multiply what with what?
R1, R2.
Exactly. So it's like, this gets loaded and the result is placed in R1, this gets loaded and the result is placed in R2. Now this multiply is going to multiply R1 and R2. And it's going to put the result in some other register R3. So the result of the multiply is going to be in R3. What's the next operation?
Gotta load B.
Yeah, exactly.
You can
So
probably load it in R1.
Yeah, loading B and put it into R4.
Okay.
So B is going to be in R4. Now what's the next operation?
Add.
Adding R3 and R4. And we put the result in a new register R5. By the way, we assume that we have an infinite number of registers at this point. Yeah. So you assume that you have an infinite number of registers, then you leave mapping this to physical registers, you leave it to which stage in the compiler?
Register allocation.
Yeah. Register allocation.
Register allocation stage, yes. So now we are adding these, and now what should be the next?
Store it in the memory
Exactly,
location.
yeah, so this is a store. The assign is just a store. So you are storing R5, so this is this is going to be in R5. So you store R5 into X. Okay. So this abstract syntax tree, it can be nicely used to generate code. And by the way, what algorithm did we apply to generate this code? What graph algorithm did we apply?
Depth first.
Yeah, it's depth first. And is it post order or pre-order?
Post order.
Reorder, right?
Where did we start processing? From the leaves or from the root?
The leaves.
Yeah, we started from the leaves, right? So it's post order. So we processed this and this, then we processed the parent. So the parent is processed after the children, which is post order. So with just a simple post order DFS, you can go from an abstract syntax tree into abstract assembly code. Okay, but now the question is not to get from an abstract syntax tree to this code. The question is, how can we get from this grammar or this parse tree into this abstract syntax tree? The point here, the key idea, is to look at the rules in this grammar and identify the rules that correspond to the operations that we care about. And whenever a reduction happens using that rule, we create a node in the tree. So if we do this, if we look at this, now here we have an identifier, so we'll just create an identifier node. Create or make, let's use make an identifier node. And here we make a number node. But here, what happens here? Should we make a node or not?
For which one?
For this parentheses expression. So in order to see this, whether we should create a node or not, if we have something like a times, what if we had a parentheses here? If we had parentheses, then what we want here is we want the assign, and we are assigning the expression to x, but this expression is in this case what?
You multiply first.
Yeah, the multiply, the multiplication of the identifier and this is another expression. So it's the add of number and identifier. So in fact, with this parentheses expression, we did not create a new node. So this is basically taking the node that already corresponds to this expression, to whatever this expression, the tree, the abstract syntax tree that corresponds to this expression. We take the root of that tree and make it this, so this is the tree that I'm referring to. So it's, our expression here is this. So this is the expression between parentheses. So we are taking the tree that represents this expression, and now the root of this tree becomes, the right operand for the multiply. So when we have parentheses, we're not actually creating a new node. Okay? And remember, what to keep in mind here, what's important to keep in mind is that this thing is recursive. So this process of parsing, the grammar is recursive, and the abstract syntax tree is recursive. So this can be when you have a rule like this, parentheses expression. This expression can be just the root of a whole big tree. So this can be an arbitrarily big expression. So it can have its own tree. So what we are saying here, we're just basically linking trees. So when it comes to something like this, we are just linking trees. So we are not making a new node here. And here, when we are making this substitution, factor goes to term, we're not creating any new operation, but the new operation is here. So we are making a divide node, making a divide node, and here we are making a multiply node. Here, are we making any new nodes? So basically these rules that correspond to substitutions, only substitutions without actual operations, basically these are the rules that are not going to appear in the abstract syntax tree. Remember, the abstract syntax tree is going to have the actual operations, and it's going to eliminate anything that corresponds to grammatical substitutions, substituting one symbol for another. So this rule here is just saying, substitute factor for term or expand term into factor. So it's not doing any actual operation. This is doing an actual operation. Make a subtract node, and this is make an add node. And in this assignment, what are we making?
The assign node.
Making an assignment node. But now, how do we make these nodes? So making a node is basically, a node in the tree will have two children. So a tree node has two children. So making this identifier node or number node, this is trivial because this is a leaf node. So this is just a leaf node. So basically we are creating a node, and in this node, think of it as an object, and this object has in it, some type, which is identifier. This is an identifier, and then it must have the actual name of that variable. Or what is more important than the name of the variable is what? When we generate code, we don't care about the name. We care about
memory location.
yeah, the memory location or the the offset of that variable. So in fact, the offset is necessary. It's necessary to keep the offset of that variable, but keeping the name, which is symbolic information, is not necessary. It will be useful, as we said in the earlier lectures, keeping the name or the symbolic information, keeping that in our data structures will be useful for what?
Debugging.
For debugging. So if we assume that we don't care about debugging, the essential thing that we need to keep is only a number, the offset that corresponds to this variable. So we no longer need to remember that it's called X or Y or Z or whatever fancy name the programmer gave it. For us, it's a number. It's a location in memory. Okay? So this is for these leaf nodes. Now these are non-leaf nodes. These are nodes that represent operations. So let's think about this. Making a multiply node. So what do we need to do in order to create this multiply node? So suppose now we created the two leaf nodes for identifier and number. That's easy. Certain objects that have some information about this variable and information about this integer, which is the value of this integer. Then, after creating these leaf nodes, what do we need in order to create this node?
Two nodes that connect to it.
Yeah, exactly. So a node has a left child and a right child. So this is a binary operation. Multiply is a binary operation. So it needs two children, two operands, the left operand and the right operand. So this is the left and the right. So it needs to know, in order to do this multiply node, we need to have a pointer to the left operand and the right operand in order to link them together. In order to say that this node has this identifier as its left child and this number as its right child. Now, how do we do this? We need a mechanism for passing variables, passing certain attributes that are associated with the symbols in this grammar. And the way we do this is we will be using the yak notation. So what is yak? Yak is a parser generator. So it takes a grammar that you write. So you write a grammar, and you write actions like these. Of course, these actions they're still incomplete. We haven't completed them, so they still don't make much sense. So it takes a grammar and an action associated with each rule in the grammar. And using this, it generates C code that does the parsing for you. So it does all of this LR1. Remember all of this LR1 stuff, the table, creating the states, and then generating the action table and the go-to table, all of that stuff that you have enjoyed in homework number 3. So that pleasurable stuff. So when you use a parser generator, you will not get to enjoy it because the parser generator will do it for you. So it will do all of that work for you. It will do all the creation of the tables and everything, and it will just give you C code. So all what you need to do is to write the grammar and then write these actions that are associated with the grammar rules. And in fact, the main objective of today's lecture is understanding these actions, what they mean, and what we need to write in order to create or build this abstract syntax tree. Okay, so by the way, this yak, so that was the first, parser generator program. Does anyone know what it stands for? Yeah.
Yet another compiler.
It stands for yet another compiler. Because it's a compiler. It itself is a compiler, and you give it the grammar and it generates a parser for you, and that parser becomes part of the compiler that you are building. Okay, so it's yet another compiler, but we will be using Bison, which is a more recent version of this parser generator. Now, using Yak and Bison, we'll be using Bison. So there is a notation that they use for each rule in the grammar. They use the symbol $$ for the left-hand side, and for the all the symbols that appear on the right-hand side, they use the symbol $, and the number of the symbol. So, for example, in this rule, so this is the $, this is the left-hand side, and on the right-hand side we have 3 symbols, 2 variables and 1 terminal. So everything counts. Remember, when we count the symbol to the right-hand side, everything counts, whether it's a terminal or a non-terminal. So term is going to be $1, multiply is $2, and this is $3. Okay? So why do we need this? We need this in order to say, okay, in order to create a multiply node, I am constructing $. So this is the node for term. The node for term is the node for this left-hand side term multiplied by the node for factor. So I express this as, so I need to know $1 and $2 or 3?
3.
3. 2, I already know that $2 is the multiplication sign. So $3 is the third symbol, which is the factor. So you will be writing things like this in the assignment. Okay. So this make node is going to be doing something like, this $, is a node that is made by linking whatever, I have the node for this term and the node for this factor. So it's going to be linking, in this case, it will be linking the node for term with the node for factor. But, when the term consists of a single factor, then what makes sense here? $, equals what? So I only have one symbol here.
$3.
$1. So this is just like a pass. Here I'm passing. So I'm not actually, creating any new node. So basically, because this is just a substitution, when you are substituting, when you are renaming a factor to a term, or you are doing this grammatical substitution, you are saying that $, is $1. Okay? And similar for the make divide. Of course, we will do at least one more example on this $sign notation so that everyone understands it. So this is the first example, but there will be more examples on using this $sign notation. But you will use it in the assignment, in the programming assignment. This is what you will be using in order to build a compiler. So in this case, similarly, $1, $3. Now this make multiplication, what will it be doing? It will be doing something like make multiply node that takes this $1 and $3. Well, in fact, these $1 and $3 for this function is going to be a regular function that takes, you know what is tricky about this dollar sign notation is that this dollar sign this attribute can have different types. So in this case, what do you think the right type is, given what we have written so far? What's the type for dollar sign?
Integer.
No, it's gonna be a node.
Yeah, it's a node. In fact, a pointer to a node.
Yeah.
Exactly. So this is what dollar sign here is a pointer to a node. So if you, it's gonna take a node pointer, node star n1 and node star n2,
Yeah. Are the
and it's going to create, create n or create new node n, and then n dot left equals n1 and n dot right equals n2, and you want to return, if it's a pointer, then you will return, in fact, the address of n. Sorry, the address of n. So don't worry about the syntax at this point. It's most likely you'll be doing this as pointers, the pointers to nodes. So basically, creating a multiply node, you are taking a pointer to a node and a pointer to a node. You create a new node that you call n, and then the left-hand side is going to be n1, the right-hand side is going to be n2, and you are returning the address of this node. Or if you create a new node, at address n or with node pointer n, then you will return n. So if you use n for the pointer, create new node with pointer n, then you will return n.
Is that that's a pointer, right? Not a multiplication at the node n1?
After,
Yeah. That's a pointer?
yeah, that's a pointer, yeah. So we are passing pointers. We are passing pointers to nodes, and we are linking them. So don't worry about the syntax. You'll have to worry about the syntax when you write the program, but not now. So focus right now on the concept. So the concept is that this make multiply node is taking two node pointers and it's linking them. And if you keep doing this, you will eventually, the last node that you will create is going to be what? If you keep doing this,
The leaf node.
No, the root node.
no, we're going from leaves to, we're going bottom up. So the last node that you will create is going to be the root node. So you create the leaves, it's bottom up, right? We are building this tree bottom up, in a bottom up manner. And in fact, because we are using this with a bottom up parser, we are implying here the use of an LR1 parser, a shift reduce parser. So what we are saying here is that whenever the parser makes a reduction using rule number 5, whenever there is an R5, call this function, okay? Execute this action. This is an action that we are embedding in the grammar. So these embedded actions are the actions that are going to build the tree. So we are saying whenever you reduce by rule 5, execute this, which means link the left-hand side and the right-hand side. Whenever you reduce by rule number 6, execute this action. Whenever you reduce by rule number 7, execute this action, which is basically nothing. We are just passing. So we are not creating a new node here. We are saying that when we do this, we are not creating a node. We are just taking this identifier, which is what the factor is. We are taking this identifier and making it this node here. So by doing this pass here, we are bypassing we are bypassing or skipping those rules, those grammatical rules that do nothing. This is a grammatical rule that does nothing in terms of actual code generation. It does something in terms of parsing. Grammatically, it's meaningful, it's significant. But in terms of code generation, it does nothing. So here, basically, we are passing the whatever this dollar sign. So this dollar sign here, we are passing it to this. It's going to be the same.
Yeah. So in that case, it would be you would use that pass notation on line 4 as well.
On line 4, yeah, exactly. So, and on line 4, for the rest of the grammar, in fact, this is very similar. So for the make add, we are doing dollar sign equals make of $1 $3, and this is dollar sign equals make subtract node $1 $3, and this is just a pass equals $1, and this is an assignment node. So dollar sign is make assignment node. Okay, and we are assigning again, the left child is going to be 1, and the right child is going to be 3. So you may think that it's always 1 or 3, but no, it's not always 1 and 3. It happened to be 1 and 3 here because we have, on the right hand side, we have 3 symbols, and symbol number 1 and symbol number 3 are the ones that matter. Symbol number 2 does not matter. So in order to show you an example where it's not 1 or 3, so if we have an if statement, for example, so if we have something like if is if some condition, then some code, else some code. Okay? Now, we need to create a node for the if, right? So now the node for the if you have an if, how many children will this have?
3.
What do we need to know for an if statement?
The condition.
The condition, that's what we need to know.
And the code blocks are both true and false.
And the code, this code and this code, right? So the then code and the else code. So this is the, the then code, and this is the else code. This is what we need to know. Everything else, we don't need to know. So in this case, we will say that, okay, so we'll have a make if that will take 3 pointers, node star condition, node star then code, and node star else code. And it's going to link them. Now here, in order to write the action, we will write equals make if of what? So dollar sign.
Condition.
So what's what's the number for condition?
3.
That's 3.
3. So you have to count all the symbols. So the trick is that you have to count all the symbols, whether it's terminal or non-terminal. So the if is $1. This is $2. Condition is going to be $3. So $3 is the condition. Then what's $4?
Close parentheses.
Close parentheses. Well, basically, you have to count every symbol, whether it's a terminal or a non-terminal. Code is going to be $5, else is going to be $6, $7. Okay. So what are the ones that we need? $3, $5, and $7. So it's not always 1 and 3. Okay. So this is the logic of these $sign symbols. Every symbol on the right-hand side has a number, and don't forget the terminals, no matter how small they are. So if this is, don't skip the little ones. Okay, so this is a small symbol. This has a number too. Okay, so any question on what we have covered so far? Okay, so let's try to finish this up. So now, we have done this, the make node. Here, what do we do here? We didn't write the action for this.
$$ equals $2.
Yeah, exactly. Equals $2. Because this is $1. This is $2. Okay? And making the number node. Now here these are leaf nodes. So they are not dependent on other nodes. So the parameters to these make number node and make identifier node. They're not going to be other nodes because these are the leaves. So they're not linking other nodes. All internal nodes are going to need their children so that they can link the children. Okay? But these are the leaves. So what do you think the parameter that we pass to the leaf, what should that be?
Number itself.
Yeah, well, here, the number itself. Here for the identifier. So basically,
$1 then?
$$?
No.
That would be recursive.
Sorry?
$.
So the leaves are different. So what do you need in order to construct this node for the identifier? You in fact need the token that comes from the scanner, because these are the ones that are coming from the scanner. The leaves, so these are coming from the scanner. The scanner classified this as an identifier, but there is an actual lexeme that comes with it, or token. So you need the token and the lexeme. And of course, the details, the programming details, you will deal with it when you write the code. But what you need here is the token. So remember, the leaf nodes are different because in the leaf nodes, you're not linking other nodes. You are just creating a node that should have information about this identifier or number. In our example, we only have identifiers and numbers as leaves. Okay. All right. So this, this $sign notation, or this way of passing values from the low-level rules to the higher-level rules. So what we are doing here, basically, we are passing the values up in a bottom-up manner. We are passing the values from the low-level rules to the higher-level rules in the grammar until we get to the top-level rule, which generates the start variable of the grammar. Okay. Now, this is how we will be creating, building the abstract syntax tree. So the idea is that whenever you reduce, the parser is going to execute this action. Remember, when the parser does a reduction, so you have, this is, you have some state here, a number of states, and then you have you reduce by something like a beta. So if what you have here, or you have some beta with states, in it. So if you reduce by a rule that says alpha is A, or reduce a beta to A, or let's call it here, beta 1, then state, beta 2 state, and so forth. So there will be a number of states. So beta consists of beta 1, beta 2, all the way to beta n. Now when you do a reduction, let's do this. So you have some state, and at some point you have beta 1, then S1, beta 2, S2, beta 3, S3. So when you are ready to make this reduction, where beta is beta 1, beta 2 through beta n, when you are ready to make this reduction, how many symbols will you pop?
2n.
2n, exactly, because I have 1, 2, 3 through n. So what you are going to do is you are going to pop off all of these. So, reducing by A, beta 1, beta 2 through beta n. So you're going to pop 2n items in the stack. And then S is going to be, the state that is here, or S top, the top of the stack after popping off. So let's call it S top, is what we get. Then we push what? If you remember what we were doing when we were reducing in the LR1 parsing?
I go to the goal.
No, we're reducing by this rule, so we're pushing.
The go-to of S top A.
Well, we have to push the A first. So first push A,
Right.
Yeah.
then we have to push
Yeah, the go-to table.
go-to of A and,
Wherever the data is.
sorry, not A and, it's the state, which is S top and A. So S top is the base state. This is the base. Remember this? Pop 2 items, push A, then push go-to of S top and A. And in fact, when you do this, and this is the code that will get generated, but you can execute the action at this point. So you just execute the action associated with this grammar. So when you reduce by this rule in the grammar, you execute this action. So whenever a reduction happens, you execute the action that corresponds to that rule in the grammar. Of course, when you shift, you don't do anything. Right? So these actions are associated with reductions. Only with reductions. And in fact, some of the reductions, we are putting like useless actions, or actions that will just pass information up. So these are pass type of actions. They will pass the information from one node in the derivation tree to the node above it, to its parent in the derivation tree. So some of them will do real actions, some of them will just pass. But with the shift, when the parser shifts, there is no action. there is no action associated with the shift. The action is associated with some of the reductions.